The object first came on my radar when you were discussing Oumuamua. I say, that's the right thing, Oumuamua, which is an object that we detected in space that you believe could possibly have been extraterrestrial. He talked about this object, Oumuamua, which is this interstellar object that he claims is either junk debris or possibly a tourist scout or a spy drone. The sense of wonder that washed over the scientific community when Oumuamua slipped through our solar system in 2017 has never truly faded. Now, years later, a seismic announcement from theoretical physicist Avi Loeb has reignited that sense of awe and apprehension in equal measure. Oumuamua has not returned, but new analyses and observations continue to spark debate. Far from being a mere echo of its previous passage, this interstellar wanderer continues to captivate researchers with unresolved questions about its nature, under circumstances so bizarre that even the most seasoned astronomers are grappling to explain what they observed in 2017. What began as a promising opportunity to study an extraterrestrial visitor has remained a theater of the unexplained, raising profound questions about the nature of reality, the boundaries of human knowledge, and the hidden architecture of the cosmos. Before we start, please engage with this content by liking and subscribing for more updates. When Oumuamua first arrived, it bore all the hallmarks of an oddity. Its cigar-like shape, its unexpected acceleration away from the sun, and its lack of any detectable cometary tail left researchers scrambling to reconcile observations with known physics. Some hypothesized that a jet of hydrogen gas had propelled it forward. Others speculated cautiously about alien technology. Yet, ultimately, the object receded into the darkness, leaving behind tantalizing mysteries, a fleeting enigma that teased us with the possibility of life or technology beyond Earth, only to vanish before it could be understood. Now, nearly 8 years later, the object named Oumuamua, Scout in Hawaiian, has not reappeared, but ongoing studies of archival data and new theoretical models keep it in focus. Probing telescopes and sky surveys first flagged an anomalous object in the outer reaches of the solar system in 2017. No new interstellar candidate has been confirmed as a return of Oumuamua, but its original trajectory and velocity continue to be analyzed, linking it unmistakably to the visitor of 2017. Without a confirmed reappearance, speculation about a new orbit is theoretical, but researchers continue to study its 2017 path, which looped beyond Jupiter's orbit, lingering in the expanse where gravity wells of the giant planets tug incessantly at passing bodies. What is most confounding to researchers is not merely the idea of a return, but the behavior observed in 2017. In addition to its curious 2017 orbital pattern, one that challenged simple gravitational modeling, Oumuamua showed intermittent non-gravitational acceleration. No new radio signals have been detected, but earlier unconfirmed reports of faint emissions are being re-evaluated. Historical data suggested faint, rhythmic pulses emanating from its surface at intervals that did not align with its rotation period. These reported emissions were at the edge of detectability, fluctuating unpredictably in frequency and intensity. At first glance, they might have been dismissed as artifacts of instrumentation or interactions with the solar wind, yet archival calibration checks and cross-validation across independent observatories could not fully explain these anomalies. Simultaneously, infrared surveys from 2017 detected subtle thermal anomalies. Oumuamua appeared to absorb solar radiation and release it in erratic flares, as if pockets of volatile compounds were being ignited or perhaps exposed. These thermal outbursts occurred without warning, and they were not accompanied by any visible plume or tail formation, as one would expect from sublimating ice or gas jets typical of comets. Instead, the heat seemed to emanate from beneath the surface, suggesting an internal reservoir or a mechanism far removed from the processes that govern ordinary solar system objects. The convergence of these oddities, its gravitational dance, unconfirmed cryptic radio pulses, and its thermal spasms, has ignited speculation that Oumuamua might be more than an inert interstellar rock. While it would be premature to declare it an artifact of extraterrestrial intelligence, the data from 2017 do not fit neatly into existing paradigms. If Oumuamua were engineered, it would represent a form of technology far beyond our own, one capable of surviving the rigors of interstellar space for millions of years and endowed with power sources or physical processes that elude our understanding. It is this possibility, dubbed the technosignature hypothesis, that has drawn both excitement and skepticism in equal measure. On one side, proponents of the technosignature view, led by researchers like Avi Loeb, point to the object's geometric regularity and its non-gravitational acceleration in 2017 as possible evidence of artificial propulsion or guidance systems. They argue that natural explanations, while elegant in theory, strain credulity when stretched over the full scope of the observations. According to this perspective, Oumuamua may have been a probe sent deliberately to monitor planetary systems, its 2017 path serving as a vantage point from which to potentially continue its observations of the Sun and its retinue of planets. Detractors, however, caution that invoking alien technology risks short-circuiting rigorous scientific inquiry. They emphasize that the universe is replete with strange phenomena, and that physics still has many secrets to reveal about icy bodies, cosmic rays, and plasma interactions. From this vantage, Oumuamua's 2017 behavior could arise from exotic combinations of minerals, volatile compounds, or charged dust that we have yet to reproduce in laboratory settings. They urge patience and detailed modeling, arguing that the true explanation will emerge as we refine our instruments and expand our data set. Yet, the lack of a confirmed return keeps the focus on 2017 data, making the situation unique but not unprecedented, as other interstellar objects like 2I/Borisov have since been observed. In response, space agencies and universities continue to analyze archival data. The Pan-STARRS and Vera C. Rubin observatories have prioritized studying interstellar objects, while the European Space Agency has explored funding for hypothetical mission studies examining the feasibility of an intercept probe for future interstellar visitors. The prospect of sending a spacecraft to rendezvous with an interstellar object like Oumuamua, indeed to perhaps land on or sample such an object, has moved from the realms of science fiction into theoretical viability. Even at the lofty speeds required, a mission launch within the next decade could feasibly reach a future interstellar object as it loops through the outer planets. The implications of such a mission are staggering. Should we find an object like Oumuamua to be natural, composed of minerals and ices fashioned by processes in a distant star system, we would learn volumes about the diversity of planetary formation across the galaxy. The chemistry of an object that has voyaged interstellar distances, unmarred by the sun's heat, preserves a record of its birthplace, giving us unique insight into the building blocks of planets beyond our corner of space. We might discover isotopic ratios that challenge our models of nucleosynthesis or novel compounds that suggest entirely new branches of chemistry. Conversely, if an object like Oumuamua proves to be artificial, the ramifications are even more profound. Contact with a craft from another civilization would shatter the paradigm of human uniqueness and open the door to questions about intent, culture, and the technological capabilities of its creators. Are we hypothetically witnessing a silent observer, gathering data and receding to wait for further instruction? Is this potential probe part of a broader network, each member scanning a different star system? Or could it be, as some have cautiously speculated, a sentinel or a harbinger, an object sent not to study us, but to watch for us, held in reserve until our civilization reaches a certain threshold? Beyond the academic and philosophical stakes, there are practical considerations as well. Unconfirmed reports of Oumuamua's intermittent energy releases in 2017 hint at a power source that could revolutionize human technology if we could understand it. The prospect of harnessing energy-packing fields or discovering new modes of propulsion holds profound promise for space travel. Even the act of executing a close-range investigation, deploying small probes, drilling into the surface, analyzing its interior, would refine our capabilities in deep space operations, robotics, and autonomous systems. The lessons learned could accelerate plans for missions to more distant solar system bodies, from the icy moons of Jupiter to the Kuiper Belt and beyond. But these hypothetical ambitions are tempered by cautionary voices. History reminds us that first contact scenarios carry risks as well as wonders. The possibility of contamination, biological or informational, haunts every planetary protection protocol. If an object like Oumuamua harbors unknown compounds, microbes, or nanostructures, we must guard against unintended exposure to Earth's biosphere and vice versa. Capsule recovery, careful containment, and stringent quarantine measures would be essential. At the same time, our response must avoid anthropocentrism. We must consider that any intelligence capable of building such a hypothetical probe may operate on timescales, ethical frameworks, and values far different from our own. Amid these debates, public fascination has soared. Responsible social media platforms overflow with theories, ranging from the eloquent to the scientifically grounded. Some claim Oumuamua could be an alien spacecraft. Others explore natural explanations like exotic ices. While the scientific community strives to separate signal from noise, the conversation, by necessity, spills into culture, art, and politics. Governments eye the phenomenon with strategic interest. An interstellar visitor, if it were to harbor advanced technology, becomes a matter not only of science, but of national security and international diplomacy. Who controls the data? Which treaties govern the study and possible recovery of such an object? Should a single nation spearhead a mission, or must it be a collective human endeavor? In universities and think tanks around the world, symposia are being convened to address these questions. Workshops on astrobiology, space law, and advanced propulsion gather interdisciplinary experts to craft frameworks for investigation and response. Some propose the creation of an interstellar object task force, a permanent body charged with monitoring, analyzing, and, if feasible, intercepting objects like Oumuamua. Others call for a new phase of citizen science, inviting amateur astronomers and enthusiasts to contribute observations, feeding into a decentralized network that can track and predict interstellar objects' every move. For the average person, the study of Oumuamua evokes a rekindled sense of cosmic perspective. In classrooms, teachers use its saga to illustrate the power of curiosity and the iterative nature of science. It is a potent reminder that the universe is far larger, stranger, and more dynamic than our everyday lives suggest. At night, amateur stargazers lift their binoculars, hoping to catch a glimpse of other potential interstellar objects, inspired by an object that journeyed from the depths of space to our solar system in 2017. Yet, for all the technical details, strategic planning, and philosophical ponderings, something elemental lies at the heart of this event: the rekindling of wonder. The study of Oumuamua, since its 2017 passage, forces us to confront our place in the cosmos, to admit how much remains unknown, and to embrace the thrill of discovery. It is a punctuation mark in the story of human curiosity, proof that even after centuries of exploration, the universe still holds surprises that defy expectation and demand humility. An undercurrent of urgency pulses through the corridors of research institutions as new analyses of 2017 data on Oumuamua trickles in. Each new spectroscopic reading, each recalibration of its past orbit, each subtle shift in its recorded brightness serves as a puzzle piece in an unfolding cosmic mystery. Yet despite our unprecedented observational capabilities, this enigmatic traveler continues to elude definitive explanation. In truth, every answer seems to summon deeper questions, and every hypothesis exposes the limits of our imagination. That paradox, where knowledge begets more unknowns, lies at the core of the Oumuamua phenomenon, compelling us to rethink not only the mechanics of interstellar objects, but the foundational assumptions upon which our understanding of the universe rests. Consider, for instance, the remarkable precision with which Oumuamua's 2017 orbit was charted. Unlike most solar system bodies, whose trajectories conform closely to the gravitational influences of the sun and planets, Oumuamua carved a path that bent and twisted in defiance of simple celestial mechanics. Small perturbations hinted at forces beyond gravity alone, faint pushes and pulls that suggested the presence of non-gravitational accelerations. In 2017, the absence of visible outgassing led many to dismiss such forces as measurement error. Now, as we reevaluate similar deviations in archival data, the case for an active internal mechanism remains under scrutiny. What could power such a mechanism in a body that has dwelled in the expanse of interstellar space for untold millennia? Natural processes such as desiccated ices turning to gas under the faint warmth of distant stars remain on the table, but they strain under the weight of repeated analyses. The chemical composition required to sustain this behavior without leaving a telltale plume of vapor or dust seems almost fantastical, reminiscent more of speculative engineered spacecraft than of simple cosmic rubble. This convergence of strange motion and hypothetical energetics has prompted some theorists to explore exotic possibilities. Among these, the notion of unique materials comes to the fore, substances capable of storing and releasing energy in ways potentially unknown to terrestrial chemistry. Hypothetical allotropes of carbon, superconducting minerals, or even aggregates of nanostructures could harbor latent power, dormant until gently coaxed by solar radiation. In laboratory settings, scientists have begun to synthesize and test compounds with ultra-high tensile strength and unusual thermal properties, seeking analogs that might mimic Oumuamua's reported peculiar emissions. Early results are tantalizing. A handful of experimental materials demonstrate mild non-thermal heating under solar illumination, though none match the intensity or irregularity recorded on the interstellar object in 2017. Nonetheless, these forays herald a new frontier in material science, one in which the laboratory becomes a proxy for the far-flung environments where such materials might form. Meanwhile, our theoretical frameworks are under pressure. Classical mechanics, bolstered by centuries-spanning triumphs in celestial navigation, now strains at its edges. If Oumuamua's 2017 movements cannot be fully captured by Newtonian gravity, we must ask whether relativistic or even quantum effects play a role. An unsettling prospect, as these regimes rarely converge on macroscopic bodies of this scale. Surely, the minute corrections described by general relativity have little sway over a loose aggregation of rock or metal. Yet the slightest deviation, observed over astronomical distances, can reshape our predictions. Some researchers have speculated that interactions with dark matter, those ghostly particles that permeate galaxies without interacting electromagnetically, could impart subtle forces over time. Although direct detection of dark matter remains elusive on Earth, Oumuamua may have served as an unwitting probe, its path potentially charting a map of invisible mass distributions across light years. Beyond physics and chemistry, questions of origin stoke heated debate. Oumuamua's galactic trajectory traces back through the cosmic tapestry, in principle allowing us to pinpoint its birthplace. Researchers have retro-computed its course, accounting for the gravitational wakes of stars and the rotating disk of the Milky Way. Preliminary maps suggest a probable origin within a dense stellar nursery in the Carina Sagittarius arm, some 500 light-years away. That region teems with young suns, protoplanetary disks, and the turbulent jets of fledgling stars. Could Oumuamua be a fragment flung out during the chaotic infancy of these systems? A cosmic bullet cast by gravitational interactions or stellar winds? If so, its voyage would have spanned eons, carrying within it a chemical archive of its birth environment. But even these reconstructions carry uncertainties. Small errors in velocity amplify across centuries of travel, and the chaos of galactic tides muddles clear backtracking. Thus, the question of provenance remains tantalizingly open. Amid the technical analyses, human dimensions weave their own narrative. The ongoing study of Oumuamua has rekindled debates over our approach to discovery and exploration. Traditionally, space missions have been scripted years or decades in advance, with meticulously detailed plans and incremental objectives. Yet, the continued fascination with an interstellar object like Oumuamua demands agility, adaptability, and the willingness to embrace mission profiles that blur the lines between scouting and improvisation. Would we send a fleet of small, rapid deployment probes swarming around a future Oumuamua to maximize data collection from all angles? Or would we risk committing to a single, larger spacecraft carrying high-precision instruments, banking on the promise of fewer but richer data sets? These strategic questions echo military doctrines more than scientific orthodoxy, prompting a cross-pollination of decision-making principles rarely seen in academia. At the same time, the public imagination surges forward, demanding to be part of the story. Crowdfunding campaigns have sprouted, pledging support for private missions, while space agencies gauge the appetite for citizen-involved research. Enthusiasts with modest backyard telescopes coordinate global observation networks, contributing photometric readings that fill temporal gaps left by professional facilities. The spirit is reminiscent of the early days of comet hunting, when amateurs charted paths across the night sky and shared telegrams of discovery. Now, armed with digital platforms and instantaneous communication, that spirit transmutes into a planetary-scale collaboration. People from Tokyo to Toronto pore over archival images, flagging anomalies and sharing theories on social media, while artists craft renderings of Oumuamua's potential interior. Some envision sleek metallic frameworks, others organic membranes pulsating with bioluminescent life. In the halls of government, these grassroots movements fuel policy discussions. Lawmakers and space administrators grapple with questions of governance: how to regulate private entities launching probes, how to share data equitably, and how to ensure that humanity's outreach does not replicate terrestrial power imbalances. International treaties, drafted in the age of the moon race, must be revisited. Clauses on planetary protection and salvage rights, once focused on Mars and the outer planets, now must accommodate a truly foreign object. The United Nations Office for Outer Space Affairs convenes working groups, while regional alliances debate whether funding joint missions could catalyze cooperation or engender competition. Not since the Apollo era has space policy captivated such a broad audience, nor has the specter of a potential alien artifact spurred such widespread reflection on our collective responsibilities. Amid legislative chambers and backyard observatories alike, a more profound conversation emerges. What does it mean to be human when confronted with the possibility of other intelligences? If an object like Oumuamua is hypothetically alive in some way, animating processes beyond our ken, does it challenge our concepts of life itself? Biologists and philosophers find themselves in dialogue. Is life strictly defined by earthbound criteria, or must we expand our definitions to include entities that transmit energy signals, store information, and exhibit purposeful motion? Across this interdisciplinary landscape, proponents of panexobiology advocate an inclusive taxonomy, one that recognizes potential life forms based on universal principles: metabolism, information processing, and evolution, rather than Earth-centric biochemistry alone. An object like Oumuamua, in this view, could exemplify a form of life or near life at the boundary between the animate and the inanimate, a gray zone that eludes simple categorization. Such theoretical expansions carry profound ethical weight. If we approach an object like Oumuamua as a potentially living entity, whether biological, mechanical, or some hybrid, we must consider rights of non-interference, akin to the prime directive invoked in science fiction. Intercept missions would require not only technical safeguards, but moral frameworks, guidelines to ensure that, in our fascination, we do not destroy or desecrate a cosmic being. This ethic of respect for the alien other challenges centuries of extractive science, urging a posture of humility and stewardship. It evokes parallels with conservation movements on Earth, where endangered species command protections against invasive research techniques. Now, for the first time, we confront the idea that a visitor from the stars might deserve similar considerations. Yet, alongside reverence, a more assertive impulse persists. The potential technological revelations locked within an object, like Oumuamua, novel energy systems, advanced materials, efficient propulsion methods, spur dreams of rapid advancement. Corporations, eager to secure patents for materials inspired by interstellar compounds, lobby for prioritized research licenses. Defense contractors eye propulsion mechanisms that could revolutionize space travel, cutting transit times to Mars from months to weeks. This technocratic momentum collides with calls for open science and equitable benefit sharing. Who will own the intellectual property derived from an object that belongs, in many minds, to all humankind? These economic and ethical tensions swirl as governments, scientists, and private entities jostle for position on a stage of interstellar diplomacy. Against this backdrop, education and public outreach assume newfound urgency. Academics and communicators strive to demystify the technical minutiae, orbital mechanics, spectroscopy, radiative transfer, casting them into narratives that resonate with non-specialists. Documentary filmmakers embark on journeys to telescopes in remote deserts and mountaintops, chronicling the ongoing study of interstellar objects across the sky. Museums mount interactive exhibits where visitors can manipulate virtual models of such objects, adjusting variables to see how different forces would alter their path. In classrooms, teachers leverage the Oumuamua saga to foster cross-disciplinary learning, weaving together physics, chemistry, computer science, philosophy, and ethics. For a generation raised on digital immediacy, the silent ballet of an interstellar interloper becomes the ultimate real-world case study in perseverance and wonder. Amidst these efforts, cautionary voices remind us that not all mysteries yield clear dividends. The history of science brims with seductive anomalies that ultimately resolved into familiar phenomena, leaving behind little more than footnotes. Could Oumuamua's ultimate revelation be less spectacular than its promise? Might its perplexing features dissolve into commonplace chemistry under the glare of more exacting instruments? This sobering prospect tempers the more extravagant hopes of contact and conveys a vital lesson in scientific humility, that nature delights in confounding our expectations, and that patient skepticism is as essential as bold conjecture. Still, for all the procedural rigors and institutional debates, there is a human story at the heart of this drama. It is the